Covariant derivative, 2. In Part 1, we derived the covariant derivative, the relativistic differential operation that satisfies general covariance and can be applied in all coordinate systems, including curved space. We also proved its tensorial nature. The derivative in Euclidean space is defined as the difference between the value at x plus delta x and the value at x, divided by delta x, in the limit delta x approaches 0. By Taylor expansion, the value at x plus dx is expressed in terms of the value at x. Let's make this relationship clear by working through the equation. After dividing both sides by delta x nu, taking the limit as delta x nu approaches 0 causes the remaining higher-order terms to vanish as well. In curved space, however, the basis vectors differ between x and x plus delta x, so the value at x plus delta x cannot be expressed directly in terms of the value at x. Therefore, we use parallel transport. Parallel transport corrects for the difference in basis vectors between x and x plus delta x, using the Christoffel symbol. This follows from the proof that the magnitude of a vector is preserved under parallel transport. Therefore, by taking the difference a mu of x plus delta x minus a mu of x plus delta x parallel, we can define the covariant derivative in the same form as the derivative in Euclidean space. This was shown to correctly transform as a tensor. In the coordinate transformation law 2, we generalized tensors to the P, Q type and derived their transformation laws. Let us look back at Part 1 and confirm what type of tensor results when the covariant derivative is applied. A, mu is a 0,1 tensor. Applying the covariant derivative gives. This transforms as a 0,2 tensor. A, mu is a 1,0 tensor. Applying the covariant derivative gives. This transforms as a 1,1 tensor. T mu nu is a 1,1 tensor. Applying the covariant derivative gives. This transforms as a 1,2 tensor. In every case, the number of covariant, lower, indices increases by 1. This shows that the covariant derivative is an operation that transforms a p, q tensor into a p, q plus 1 tensor. From here, we will derive the covariant derivatives of tensors that are important in general relativity. T mu nu, T upper mu nu, and T upper lambda, lower mu nu kappa. The procedure is the same as in Part 1, so please pause and verify each step at your own pace. Derivation of the covariant derivative of a 0,2 tensor. Derivation of the covariant derivative of a 2-0 tensor. Derivation of the covariant derivative of a 1-3 tensor. Covariant derivative of a scalar. A scalar phi is a physical quantity that has magnitude only in no direction. Since it has no direction, it is not affected by changes in the basis vectors. There is no basis change to correct for, so no gamma term appears. And the covariant derivative reduces to the ordinary partial derivative. Applying the chain rule under the coordinate transformation x to x prime. This agrees with the transformation law for a 0-1 tensor. Since a scalar is a 0-0 tensor, applying the covariant derivative yields a 0-1 tensor. This is consistent with the rule that the covariant derivative transforms a p, q tensor into a p, q plus 1 tensor. Covariant derivative of the Kronecker delta. We will now look at the covariant derivative of the Kronecker delta. Delta upper mu, lower nu. Since this is a 1-1 tensor, applying the covariant derivative gives a 1-2 tensor. That is, we use the covariant derivative formula for a 1-1 mixed tensor. We substitute delta mu nu for t mu nu. The Kronecker delta is defined as follows. The first term on the right-hand side is constant, so it is 0. Here the second and third terms reduce by the Kronecker delta as follows. and the covariant derivative of the Kronecker delta is 0. Since the Kronecker delta is a tensor whose components are all constants, this result is natural. Covariant derivative of the 0, 2 metric tensor. Let's check what happens to the metric tensor g mu nu under a covariant derivative. Since g mu nu carries two lower indices, it transforms exactly like a general 0, 2 tensor. Here we substitute the definition of the Christoffel symbol of the second kind. The metric products inside the parentheses reduce to the Kronecker delta. Now we substitute the right-hand side of the Christoffel symbol of the first kind. Since the metric tensor is symmetric, g mu nu equals g nu mu. All 6 terms cancel in pairs, giving nabla rho g mu nu equals 0. The covariant derivative of the metric tensor vanishes. Covariant derivative of the 2, 0 metric tensor. Now let's look at the covariant derivative of the 2, 0 contravariant metric tensor. It follows the same form as a general rank 2 contravariant tensor. Recall that the Kronecker delta is defined by g mu alpha nu equals delta nu mu. Taking the covariant derivative of both sides, applying the Leibniz rule, we already showed that the covariant derivative of the 0, 2 metric tensor vanishes. So the first term drops out. Multiplying both sides by g beta mu. Nabla rho g beta nu equals 0. So the covariant derivative of the 2, 0 contravariant metric tensor also vanishes. The physical meaning of nabla g equals 0. The fact that the metric tensor vanishes under a covariant derivative is called metric compatibility. And it carries deep meaning in relativity, with implications that reach in many directions. Here, we'll focus on 3 of them. The metric tensor g mu nu plays the role of translating coordinate-dependent apparent values into the true physical distance. No matter which coordinate system you use, the actual physical distance, the line element squared, ds squared, is exactly the same for everyone. It's an invariant. So is this ruler, the metric tensor itself, still reliable as we move through spacetime? That's exactly what the covariant derivative nabla rho g mu nu measures. How the metric, our standard for inner products, fundamentally changes as we move an infinitesimal distance along the direction x rho. The result nabla rho g mu nu equals 0 tells us that no matter what path a vector is parallel transported along in spacetime, its length and the angle between it and another vector, that is their inner product, never change, no matter how curved spacetime is. The metric's reliability as a ruler never changes, anywhere in the universe. This is the first meaning of metric compatibility. Let's confirm this with the math. Now let's unpack the decisive meaning behind this statement. The length and angle of vectors are preserved under parallel transport. We'll do this using the calculation of the covariant derivative. Let's take the covariant derivative of the inner product of two vectors a mu and b nu. That is, the scalar g mu nu a mu b nu, along the direction x rho. Since the Leibniz rule applies, this expands into three terms. Applying nabla rho g mu nu equals 0. The first term vanishes, and the equation becomes as follows. This result carries the following important geometric meaning. Parallel transport preserves length and angle. In relativity, the operation of carrying a vector straight, that is parallel, along curved spacetime is called parallel transport. When vector A is being parallel transported along a given path, its covariant derivative along the direction of that path x rho is 0. Nabla rho a mu equals 0. And likewise nabla rho b nu equals 0. In the derivation, we applied metric compatibility. Nabla rho g mu nu equals 0. As a result, it follows automatically from the equation above that nabla rho g mu nu a mu b nu equals 0. The change in the inner product is 0. Length. Let's replace b nu with a nu here. Nabla rho g mu nu a nu equals 0. G mu nu a nu is nothing other than the square of the length of vector A. The fact that its covariant derivative vanishes means that even when vector A is simply parallel transported, its length doesn't change. Angle. Now, if a, mu and b nu remain distinct vectors, then g mu nu a mu b nu is the inner product of the two. And using the lengths a and b, we can define the angle theta between them as since neither the inner product g mu nu a mu b nu nor the lengths a and b change under parallel transport, cosine theta doesn't change either. In other words, when vectors a and b are parallel transported together, the angle between them stays the same. If nabla rho g mu nu were not 0, the very standards of length and angle would drift arbitrarily as you move through space. And you couldn't even properly define a shape anymore. Let's look at the second important meaning of metric compatibility. The covariant derivative of a rank 2 covariant tensor is given by the following. Since nabla rho g mu nu equals 0, the equation above can be rewritten as follows. Now, let's cyclically permute the indices in equation 1 to get two more. Permuting the indices of equation 1 as rho to mu, mu to nu to rho, and renaming the dummy indices lambda to beta and alpha to lambda. Permuting the indices of equation 1 as rho to mu to rho, nu to mu, and renaming the dummy indices lambda to alpha and alpha to beta. Here, using the fact that the Christoffel symbol is unchanged when its lower indices are swapped. Gamma lambda mu nu equals gamma lambda nu mu. Let's compute 2 plus 3 minus 1. To eliminate the metric, g beta rho, remaining on the left-hand side, let's multiply both sides by the inverse metric. The metric with upper indices, g rho sigma. This gives us the Kronecker delta. G beta rho g rho sigma equals delta sigma beta. We'll also divide both sides by 2. This gives us the formula for the Christoffel symbol. Specifically the Christoffel symbol of the second kind. In fact, we already derived this same Christoffel symbol earlier. From a completely different angle. The parallel transport of vectors. The starting points were different. Yet we arrived at exactly the same equation. The rule for carrying a vector straight. And the rule that the ruler is the same everywhere. These two could, in principle, have been decided independently. And yet the universe has adopted only one rule. That satisfies both at once. That rule is the very Christoffel symbol. You've now derived in 2 different ways. Here, the law that the standard of our ruler never breaks down anywhere in the universe. Nabla rho g mu nu equals 0. Has given us from a completely different angle. The Christoffel symbol. The very key to unlocking gravity. Let's look at the third important meaning of metric compatibility. The metric tensor, g mu nu, plays the role of converting a contravariant vector into a covariant one. That is lowering an index. A, nu equals g mu nu a mu. Thanks to nabla rho g mu nu equals 0. It doesn't matter whether we take the covariant derivative first and then lower the index using the metric, or lower the index using the metric first and then take the covariant derivative. Either way we get the same result. This means the metric tensor can slip through the covariant derivative and act on the other side. Let's look at this with a concrete example. Proof by calculation. Let's consider the operation of lowering the index of the contravariant vector, a, mu. That is turning it into the covariant vector a nu. Pattern A. Lower the index first. Then take the covariant derivative. First, we lower the index to form a nu equals g mu nu a mu. And then take the covariant derivative of the whole thing. Nabla rho. Here, we apply the product rule for covariant derivatives. The Leibniz rule. The equation splits into 2 terms. Now we bring in the key premise we've been focusing on. Nabla rho g mu nu equals 0. This makes the first term on the left vanish completely. Pattern B. Take the covariant derivative first. Then lower the index. Let's take a closer look at the expression g mu nu. nabla rho a mu, which remained from the result above. This represents exactly the operation of first taking the covariant derivative of a mu, that is, nabla rho a mu, and then multiplying by g mu nu to lower the index. Conclusion: placing the two patterns side by side, we can see they match exactly. This proof is logically sufficient on its own. But let's watch with our own eyes whether the metric tensor really does slip through the covariant derivative. This calculation also serves another purpose. It checks that the sign convention is consistent, even though the Christoffel symbol flips sign, between covariant and contravariant vectors. The equation we want to prove is the following. Let's replace the left-hand side with the covariant derivative formula for a covariant vector, and the right-hand side with the covariant derivative formula for a contravariant vector. Let's expand the right-hand side of equation 2. Let's rewrite the first term on the right-hand side as follows. Let's substitute this into equation 3. Now let's substitute the expression we derived from the metric compatibility condition into the second term of equation 4. The Christoffel symbol of the second kind in the second term on the right-hand side contracts down to a Christoffel symbol of the first kind. The third term, using the metric, can be written as the covariant vector A lambda. The fourth term, just like the second term, becomes a Christoffel symbol of the first kind. After renaming the dummy index from sigma to mu, it cancels with the second term. Let's go back to the equation we wanted to prove. Equations 1 and 6 are exactly the same. And with that, we've proven that the left-hand side equals the right-hand side. This means the metric tensor g mu nu can slip through the symbol of the covariant derivative, nabla rho, as if it were nothing more than just a constant. Without this property, Einstein's field equations could not be derived. We've now covered the topic of the covariant derivative across two parts. The covariant derivative, nabla rho, was a tool for capturing true change that doesn't depend on the coordinate system. This becomes an unshakable foundation for the path ahead, leading to Einstein's field equations.